We are going to discuss the idea of free fall and non-free fall by looking at the idea of terminal velocity. We can discuss what is free fall and what is non-free fall, but it's more fun doing it this way. So in order to talk about terminal velocity, I want to go a few years into the future, a future where somebody from our class has become a multi-billionaire because of his tech skills. So it started off in 8th standard with some small program to kind of use an AI like bot to take him to the online classes during the COVID pandemic. And from there, it went leaps and bounds, and he became the foremost programmer of the era. And because of the different kinds of breakthroughs in AI technology that he fostered, he's become a multi-billionaire with dozens of patents to his credit, which are used by companies all over the world.
And my and a classmate from here is my assistant.
Kuch bhi, nobody's going to work for you, okay? I can guarantee.
No, my friend Ishan. We both learned programming together, okay?
Just go along with the story, man. Okay.
Okay.
So Snehashi is a billionaire and he doesn't have to do much work anymore. Okay. 35 years down the line, he's done it all. And all he does now is just like follow his passion. And one of his passions is skydiving. Okay. So he gets on a plane every other week, goes off to whatever 20-30,000 feet, and then jumps off the plane with a parachute, of course. So as Snehashish is falling off the plane with a parachute, I'm going to try and draw Snehashish paragliding. Okay, I mean not paragliding, diving, paradiving, and yeah, let's see how this kind of turns out. It's kind of okay on the blackboard. I don't know how it's going to look over here.
Are those hands?
Yeah.
I see
Sir,
it.
is he paragliding or is he skydiving?
Skydiving.
Okay.
Paragliding, you jump off the ground, I think.
Hey, I'm going to be fat. I'm going to be old, so I'm going to be a little fat. No.
Yeah, he's become a little fat because of all the food that he's been eating and doing nothing.
Yeah.
Sir, this is a wrong diagram, sir.
Bad man.
And
sir, you have to be ulta, sir.
I forgot.
Do you think the parachute will fit?
Yeah, I forgot to put the parachute. So this parachute has a belt and all that. And
that looks like real.
Sir, one question: have we moved on from friction, or are we?
Wait. Hold your horses.
Okay.
Sir, his knees and elbows have to be bent upwards, sir.
You can't.
Doesn't
matter.
This is a rough diagram, yeah.
You have all the experience and all that.
Okay, no problem. Okay, so he's what did you say? This is skydiving.
Skydiving.
So he's skydiving.
The skydiving is so costly. I won't waste my money on skydiving.
You're a
Dude, you're a billionaire.
Yeah, but still I won't.
You know how many zeros are in a billion?
You have your own plane.
You know, billionaires get
Yeah, I don't care. I would rather help the poor with that.
Shut up, Sneha.
We'll see about that.
You are helping. Don't worry.
What you are doing right now is for the sake of physics.
That's nice.
You're doing
for the sake of physics. Let's say for the love of physics. Okay.
Okay, so what are the forces that are acting on you as you're falling down? So you're kind of thinking about that's not your nose, by the way. That's just the okay. Maybe
that would be so ridiculous.
Okay. So then okay, quite now. Let me proceed. So as you're falling down, you're kind of thinking about your old physics teacher who taught you something about forces under the influence of gravity as an object is moving, and you're thinking, you know what, I'm falling downward towards the earth because of the pull of gravity, and that pull of gravity has a value of about my mass
9 point,
multiplied by the
yeah,
gravity
mg.
constant. But as I am falling down, there is wind that is there against me, right? I am increasing my speed at the rate of something like 10 meters per second every second. So 10 meters per second square approximately. This is my acceleration, right? So the net effect of all these forces hitting your body, right? There are tiny forces of the wind kind of like pushing against your body. And that adds up, all these tiny forces adds up to a larger and larger force. And this of course is the what we call as air drag. Okay, so this
Drag, yeah.
is called as air drag. Okay, now the question that has to be asked is, as you are falling down, you are going to become faster and faster. What is going to happen to this air drag? Okay, what is going to happen to
Is that an open question?
force because of air? Sorry, Ishan, can you repeat that?
Are you asking a question to us?
Yes.
Oh, yeah, it will increase now.
Yeah.
Okay, so initially mg is going to be greater than the air drag. Okay, as he accelerates, mg sorry, I should write the force because of the air drag will increase. Okay, do you all agree with this? This is all logical.
Yeah.
Yes.
It all makes sense, right? Okay, so now I ask you, will air drag increase forever? Will it keep increasing?
No, sir.
You don't think so? You think there is a certain
yeah.
limit? Yeah, tell me.
So, like, I think when he deploys the parachute, the air
No.
drag will.
Think, for example, that he's not opening the parachute. We are just talking about the situation as it is. The parachute is just so he doesn't die. But let us just think about it. Snehashish is thinking while he's falling. He's remembering his 8th standard physics class. And these are the thoughts that are going through his mind.
Sir, the air will also.
Yeah, tell me.
Sir, because there'll be too many air molecules in one place and air molecules are equally spread out. They will also move away, right?
Yeah, they will eventually have to move away because he is a solid object falling through fluid space, air. So the air molecules will move away. But anybody who has just stuck their hand outside a window while the car was driving on an empty highway knows very well the effect of how much air comes on your hand, right?
Yeah.
Yeah, so there is air drag which is there even when you're going in a car. Remember, he's diving from something like about 20,000 feet or more, right? So as he is accelerating through the air, he's going to feel the air drag. He's still falling down. But the point that we have made is the air drag will keep increasing, but there is a limit to the amount of air drag that it can go up to. That's what people are saying. So now I'm asking you, what is that limit? So
wait, when did we say there was a limit?
Sorry?
How is that?
Kailash thinks that there is a limit.
Yeah, Kailash said that he thinks there is a limit.
Okay. Why is there a limit?
That's my question.
Good.
If somebody disagrees, then you say, why do you think the air drag will not have a limit, upper limit?
It's like how friction has a limit.
You are comparing it through an analogy. You are saying friction, static friction has a maximum value beyond which it moves.
This is kind of like friction. Yeah, this is kind of like friction because it's holding it back, right? Like it's doing the same thing that friction does, except it's doing it vertically.
But what's the reason?
Yeah.
And
but
then
what's the
it's
reason?
like how friction.
Yeah, that's the point. Like, what is the reason? Hey, I forgot to put a GoPro camera on.
Like there are no two surfaces here, right? So you can't justify that.
No. So whenever we are confronted with situations like this, where we are not able to decide whether there is an upper limit or there isn't upper limit, what you can try to do is you can say that, okay, let there be an upper limit, okay, or say let there not be any upper limit. So what is the weird thing that will happen? So if there is no limit, then what could happen?
You will come in equilibrium, right? Float in the air.
So equilibrium is one of the points to consider, right? So we can think in terms of what will happen when there is an equilibrium, sigma f is equal to 0. That is, if the force of air drag keeps increasing, what will happen when mg becomes equal to air drag? Okay, and see if this leads to an absurd situation that we know is practically not possible. Okay, so when mg becomes equal to the force of air drag, then sigma f is equal to 0. Okay, which can lead us to conclude whether there is an upper limit to the air drag or not. But then, are we clear about what happens when sigma f is equal to 0? Is this possible or it is not possible? I'm waiting for all the Aristotles to come tumbling out.
Wait. See, but it depends, right? It depends how fast is FA increasing?
No, it doesn't. I'm saying that let us say that there is enough of a drop for FA to keep increasing, because we are saying if you go faster and faster, the air will hit against you more and more. So when that happens, naturally the air drag increases. So let us assume that the air drag continues to increase. So it has to pass a point where it becomes equal to the gravitational force. Okay. So when it becomes equal to the gravitational force, let me finish.
Okay.
That means that mg will be equal to fa. So if we are taking only these two forces at the moment into consideration, and we say that if these two forces are equal, then there is equilibrium. Sigma f is equal to 0. Maybe for a small moment of time, maybe for a few seconds, maybe for minutes, we don't know, but there is equilibrium. Is this situation practical, understandable, impractical, cannot happen? Please be careful about your Aristotles. Yes, now Ishan.
Yeah, but then gravity is accelerating at 10 meters per second square.
Yeah.
What if F is accelerating at something which is less?
Yeah, that is what. So therefore, what will happen is, as long as one thing is gravity is a force. You are comparing their accelerations. Is it?
Yeah.
Acceleration produced by mg. Yeah. So mg is producing an acceleration approximately equal to 10 meters per second square in the downward direction, and fa is actually retarding the acceleration, right? fa is acting in the opposite direction. So net acceleration is going to be slightly less than 10 meters per second square, and the net acceleration will keep reducing. If fa keeps increasing, the net acceleration will also reduce. Okay, so if you are interested, I'll just write acceleration net is equal to acceleration produced by mg, or let me put it like this: acceleration produced by mg minus the acceleration produced by the fa, the retarding force. So as this becomes higher and higher, this is going to remain constant. Okay, so this become lower and lower.
Yeah. So we are saying that acceleration of FA is accelerating.
Acceleration caused by fa is opposing the acceleration caused by gravity. Right?
Okay.
So again, can somebody now look at this and tell me, what do you understand from that? Sorry.
Sir.
Yeah.
After, like, there has to be a point where it comes to equilibrium.
Yeah.
After that, if the air drag increased,
Yeah.
and the mg was less than the air drag, then
Yeah.
you should be going in the opposite direction, right?
Yeah, so that creates one absurd situation. It won't happen to Snehashish, but it does happen to hailstones. Hailstones actually build up in their size because of that particular reason that you just said. There are actually updrafts, winds that are blowing upwards because of weather conditions. But in this case, there isn't any weather condition that are blowing winds upwards. It's nice, beautiful, sunny day. Weather is perfect. You expect Snehashish to do skydiving on any other day than a perfect day. He chooses the perfect day to skydive. Everything is beautiful. He's just jumping down, there's air against him, and he starts thinking about class 8 physics. Okay, so the sigma f is equal to 0 doesn't seem like an absurd situation. It seems perfectly understandable. You mean to say that as he falls, when sigma f becomes equal to 0, he just gets suspended in midair?
Sir, I have a question.
I think it'll pass. I think
Sir,
it'll pass.
I have a question.
I have a question.
Sir, are we in dynamic equilibrium?
Yeah, dynamic equilibrium.
Okay, there are some contrarians, non-Aristotelians in the class. Yes, questions. I can't see the hands raised, so somebody will have to make a sort of series of people to ask questions. Go ahead.
Sir, Prakriti, Kailash, and then me here.
Okay, go ahead, Prakriti.
Yeah, I was just asking, could it be in dynamic equilibrium?
Yes, what do you mean by that?
So, like both of them, mg and fa, could have the same absolute value, but they could be accelerating. They could still be accelerating in the same. I mean, their acceleration's value could also be the same. Like the absolute value of their acceleration could also be the same.
Okay, so what is happening to Snehashish? Is he suspended in midair?
No, he's moving in constant velocity.
That's what I wanted to say. He's moving in constant velocity. Well done. Next. Kailash.
Okay, so yeah, sir, I think I still think that the air drag does not reduce. It only increases for a while, like until the parachute opens.
No, don't talk about the parachute opening. Let's worry about the parachute opening later. Like I said, that's just so we don't kill Snehashish.
Yeah.
Yeah. Okay.
Talk about the situation as he is falling down. So you're saying
I'm still above the parachute leaving.
The force of air drag keeps increasing until it becomes equal to mg. But you're saying it can
almost equal to.
Almost equal to. Okay. So that part practically it may become more, it may become less. So there will be something dynamic happening at that time. But we are discussing it in a physics class, so we can talk in terms of some ideals. So they can become equal. Got it. You agree with what Prakriti said just now? That they are going to be, not Prakriti, sorry, Hiya said just now.
Sir, it was me only.
Prakriti, sorry. That it will become in dynamic equilibrium and the velocity will not change. So he will continue to fall in constant velocity, right?
Yeah.
Good. Next.
Sir, I have a question. Sir, I think that her acceleration will, Snehashish's acceleration will decrease, not increase.
Yeah, net acceleration will decrease, yes, until it actually becomes 0. When the two opposing forces become equal in magnitude and they are opposite in direction, then the net acceleration, which will be the result of this, that net acceleration can actually become 0. So there is no more acceleration, so he will be falling with constant velocity. I hope that point is clear to you and everybody else.
Yeah, sure.
Yeah.
Great. So this velocity with which he is falling, okay, so now let's talk about the velocity. So because of this, there is a certain velocity, since velocity is also a vector, maybe I can draw a really long one, because he's going quite fast, you see, at this point of time. So this special velocity with which he happens to be falling is actually called the terminal velocity. Okay, and it could be something in the region of, let's say, 200 kilometers per hour. Wait, why should I put in terms of kilometers per hour? We can put it in terms of meters per second. Let's say it's about 150 meters per second. Okay, quite a terrific speed. I'm just putting a rough value. It's not actually equal to that. You can figure that out. Look for terminal velocity in skydiving. You'll find it. So now Snehashish is a fellow for greater thrills. 150 meters per second is really not, his thing. He wants to go faster than that. So what should he do?
He can reduce his surface area.
Yes.
Yeah, that will decrease the drag.
Decrease the drag. So the surface area that he is presenting to the air can be reduced. And how he can do that is he can I'm going to draw a slide.
So he can bend his limbs.
Yeah, you can not bend his legs.
Make
Like
himself into a ball.
What he can do is he can tuck his hands in.
Yeah, yeah.
Okay, so I'm drawing. I made him look like something like Iron Man, but it's okay. Iron Man, that old armor. Okay, when he does that, and then also he can kind of change his posture, rotate himself a little bit, so he's like facing down in this direction, and then
At 45 degrees.
Again, yeah, something like 45 degree. So again, what will happen is the surface area will reduce, the air drag will become lesser. Okay, so the air drag will kind of reduce, and again he will start accelerating, right? So the acceleration will again continue until the air drag again becomes equal to mg. But by that time, what would have happened is that the terminal velocity would have reached a higher value. Say it would have become 250 meters per second.
So what would happen if I would turn at 90 degrees angle?
Yeah,
like,
exactly.
Just straight.
You can also become this angle, and you can also curl up into a kind of cannonball. Hold your legs like that. I don't know what people do. Okay, so if you let me just finish this point. So if you do that, then what will happen is that you will reduce the surface area to a minimum and provide the least surface area for the air drag. And in that case, maybe you can go faster than that. But then by the time you will be nearing the point where you will have to open your parachute. So you open your parachute and have a nice descent down to the ground. So that is the concept of terminal velocity. Okay, and obviously terminal velocity is something that not just occurs to people doing skydiving from airplanes, but obviously any object that is falling. If you give an object sufficient amount of time to fall, all objects will attain some terminal velocity. Okay, now one quick example is you go to the top of your building if it's a 3-story or a 5-story building, but ideally you want to go to a high-rise building which maybe has 15-20 stories, and you have with you a table tennis ball, okay, and a tennis ball. So you have a table tennis ball and you have a tennis ball. Now if you drop these two balls, which one will reach terminal velocity faster?
Table tennis.
Table tennis.
Yeah, table tennis.
You can easily imagine that the table tennis, although the surface area for the table tennis ball is less than that of the tennis ball. But the critical difference is that the mg for the TT ball is less than the mg
of the tennis
ball.
For the tennis ball. Okay, so that is why it will take more time for the tennis ball to reach terminal velocity than it does for the table tennis ball.
Also, mass and the surface area both are lesser in that. That's
yeah, surface area is not the only one, because surface area is lesser for table tennis ball. So you might think that it will go longer before it reaches the terminal velocity, but the mass is the greater.
Mass also matters, right?
The weight, we shouldn't say mass, mg. So
Sorry.
the weight of the TT ball being lesser, it will reach terminal velocity faster than the tennis ball. So therefore, the lighter the objects are, the sooner they reach terminal velocity. And that is the reason why a feather and a piece of paper dropped at the same time, the feather reaches terminal velocity sooner. Okay, so that's all about terminal velocity today. Tomorrow we will discuss the, next time we meet, we will discuss, let me finish. We will discuss some implications of the terminal velocity in terms of free fall and non-free fall. That we will see in the next class.